Welcome to Dr. Fred Bell's Health, Science, and Energy Show, April 4th, 2008. Tonight we have a very honorable guest on, Michio Kaku, and he is the Henry Samot Professor of Theoretical Physics at the Graduate Center of the City of New York, University of New York. He is the co-founder of the string field theory, and he has written several books, and which I'm going to congratulate him now because I think a week or two ago you hit the New York bestseller list. Thank you. Welcome, Dr. Kaku.
I'm glad to be on your show.
Yeah, I've been trying to get you on here for a while, but I guess it couldn't happen until we had the physics of the impossible.
That's right. The book shot up to number 12 on the New York Times bestseller list, and it's the number one science book in the country right now. So my publisher is jumping up and down for joy.
Yeah, she's a really nice lady over there, and it's a great company. I've actually had a couple of books published over back on Doubleday days a few years ago, so they're great people to work with.
Right.
And you were just out here. I heard you had a sellout at Caltech. While I was back in New York, you came out on my turf. And
yeah, every place I've been, Seattle, San Francisco, Los Angeles, Washington at the Smithsonian has been sellout. We've had to turn away people. We turned 100 people away in San Francisco.
Wow. Wow, we got to get you on some of these other circuits. Do you ever have time to do any teaching anymore?
Well, I'm mainly a research physicist. I work on, Einstein's unified field theory, the theory of everything.
Right.
That gives me plenty of time to think on the airplane, to think when I'm speaking and doing things and talking to people and answering questions. So I find it actually invigorating to travel and have a refreshing look at reality.
Yeah, and I loved your book, Parallel Worlds. I recommend it to everybody. In hyperspace, and you kind of lightened up on this one, making it. I think I was telling your publisher the other day. I was saying you've really learned how to write down to people where they can understand it. That's a gift,
Well, thank you. I mean, I keep remembering myself as a young boy with Albert Einstein as a role model, and the other role model was when I was watching the Flash Gordon series. I realized very early in life that I didn't have blonde hair, I didn't have muscles, but the person of Dr. Zarkov, the scientist who invented the starship and the city in the sky, that character really fascinated me. And so when I wrote Physics of the Impossible, I kept thinking of the wonderment that I felt as a kid watching Flash Gordon. Today they watch Star Wars and Star Trek and the Terminator series, but I had so much fun as a child. And now I'm a physicist, so now I can really answer the questions that children ask about force fields, ray guns, invisibility, and teleportation.
Yeah, those are amazing. When I was a kid, I read Arthur C. Clarke and Richard Heinlein and all those guys. I had a similar background. I was at the University of Michigan working with one of the paperclip physicists, Dr. Katz. And I worked in the Randolph Laboratory. We had the old cyclotron, synchrotron, and bevitron. But then they took the Randolph Laboratory, they tore it down. It doesn't exist anymore.
Oh, I see.
I was really bummed out. Then I went in the Air Force, and they made me, I don't know what they made me in there. I was in all kinds of crazy projects. And later on, I got to work over at NASA with Werner von Braun on the Apollo and the Saturn. So we have a similar spacecraft background. So anyway, I guess you pretty much described how you got here, and I've been reading through this book. When you wrote the telepathy, one big thing that's out there now is everybody's getting holographic and quantum. Everything is quantum and holographic. It's getting to be almost a buzzword out there. Now, I wanted to go through this book a little bit with you. What's some of your favorite stuff in here you like to talk about? Because you cover about everything.
Yeah, the stuff that's hitting the pipe real fast is, for example, invisibility.
Right. I just was open to that. I was just waiting for that.
Right. The Pentagon is funding it. We had a breakthrough 2 years ago at Duke University. I used to teach in my optics class that invisibility was impossible. It's impossible for light to wrap around an object and reform at the other end as if the object wasn't there. Well, 2 years ago, they did it at Duke University with microwave radiation. This was impossible. Every physics textbook on Earth says that optics does not allow light to wrap around an object. And, well, they did it at Duke University, and also Caltech now has demonstrated the same phenomenon with visible light.
Right, and that's in the metamaterials, as you talk about it.
That's right. And with metamaterials, we can actually bend red laser light and blue-green laser light in a way consistent with invisibility. So I think that within a decade, we'll actually be able to make an object totally disappear under one color. After that, the three primary colors. And after that, Harry Potter, watch out.
Oh, yeah, I totally agree. I remember what really struck me is I was on, I'm a popular science kind of guy and the Scientific American magazine reader, but the Popular Science magazine about a year ago had something. I remember they were using the camera system where they would take a picture of the sky and project it on the bottom of some of these. That was one idea. Mm-hmm. But then they showed a car, and it looked like the car was partially invisible. I mean, it was pretty amazing. Did you remember that episode or that magazine when it came out?
No, I don't remember that episode.
Okay.
But, this is real invisibility. The
right.
way that we thought it might be done, but maybe we said, nah, can't work. And now the Pentagon is really, thinking about invisible soldiers, invisible airplanes. It wouldn't quite be like the cloak of Harry Potter. It'd be more like a cylinder. Light would wrap around the cylinder, reform at the other end, so any soldier inside the cylinder would be invisible. It would work except for his eyeballs. He has to look outside. He would have to cut out two holes in the cylinder so that he could look out, and then he would see two floating eyeballs. It's like Harry Potter with two eyeballs floating in midair.
Yeah, just the opposite of the Invisible Man, where you see the black areas where the eyes, when he has the towel wrapped around him with the bandage wrapped on him, you see the black spots.
Right.
That's pretty good.
And but there are countermeasures, by the way. This is not going to be the collapse of civilization when thieves become invisible. You can throw sand over the Invisible Man, and you can see the outline of the Invisible Man, or you could put a bed sheet over him, and you can also see the outline. So there are some drawbacks to invisibility. It's not the foolproof weapon, but it is something that we physicists dreamed of, and now it's within grasp.
Yeah, it's amazing. What do you think? I would say within 5 or 6, maybe 10 years at the most that they're going to be, they probably have a suit like that. What do you think?
Yeah, pretty soon. The question is whether they can get all three primary colors to work right. Each color is a little bit different.
Right.
You may have to interweave three metamaterials simultaneously into one substance to bend red light, blue light, green light. But again, these are technical problems, and with enough time, with enough money, they should be solved. And so, but a cloak, however, would be quite difficult. A cloak is made out of fabric. It bends light in a very, very complicated way. So a cloak may be a little bit harder.
Yeah.
But an invisibility cylinder that would make anything inside invisible, like a car or a tank, that could be coming pretty soon.
Yeah, that'll be amazing. I imagine people driving down the road with a couple of those things.
Yeah, right. And, pretty soon we may not even need cars. Teleportation is making significant breakthroughs. We don't have it quite like Star Trek yet. But, believe it or not, we can teleport particles of light 100 miles from one Canary Island to another Canary Island. The next, we'll teleport a photon to the space shuttle. This is already being talked about now. Teleport a particle of light to the space shuttle. After 2020, we'll do it to the moon, once we go back to the moon.
Oh, yeah. Yeah, I've seen some of the experiments with the classic channel and then the polarized filters and then the photons sent in opposite directions. Could you explain that to the audience a little bit, how those, like Alan Elaine did some studies a while back and a few other guys. Could you explain to the audience out there a little bit how that works?
According to the quantum theory, everything vibrates. It really is true. Everything vibrates in the world. And if two electrons vibrate in unison, that's called coherence. And then if you separate these two electrons, there's an invisible umbilical cord. An invisible umbilical cord that connects these two electrons. Even if you separate these electrons by thousands of miles, you jiggle one, and in some sense, the other electron senses that presence. And that's how we do it. And then we have a third particle that vibrates with the first and then moves to go to the second particle. So it takes three particles to make it work. Now, we've done it with beryllium atoms now. We've done it with cesium atoms. And I think within a decade, we'll do the first water molecule. And after that, DNA, organic molecules. I think in a few decades, we'll be able to teleport maybe a virus. Living materials will be teleported.
That'll be really interesting to see how it, because everything is life and life is a vibration anyway. It ought to work theoretically.
Yeah, and this raises a question. If Captain Kirk is teleported from A to B, you have to destroy the original, to create this new Captain Kirk over there.
Right.
And, well, then what happened to the soul? Because the new Captain Kirk says, I have the memories, I have the information, I am Captain Kirk. But you just saw the original die. So you really begin to wonder, what is personality? What is soul if somebody over there has all your memories, all your neural circuits, all your DNA and genes, but he's really not you?
Yeah,
that really makes you think.
It's a matter of how the spirit moves, the consciousness moves through the whole thing, you know?
Yeah, that's going to be an interesting question. But however, to be fair, we can't teleport Captain Kirk yet. A body consists of 50 trillion cells. That's an awful lot of cells. And we haven't even teleported one cell yet. But Star Trek takes place in the 23rd century, which is plenty of time, I think, for us to attain teleportation.
Yeah, I like your in all your books you carry a theme through there of 3 stages or classes of civilizations. Mm-hmm. One that can harness planetary energy, one its local star, and one the entire galaxy.
Right, type 1, type 2, type 3.
Right. Could you explain that so that, by the way, everybody listening out there, we're not doing call-ins, but you can go to the fast chat on BBS, and I'll answer some of the questions or ask Michio which questions that I can as they come through. So, so go ahead and explain that to him a little bit.
Okay, well, when we physicists seriously look for extraterrestrial intelligence in outer space, we don't look for little green men. We look for type 1, type 2, type 3 civilizations. A type 1 civilization is planetary. They can manipulate the weather. They can change the course of volcanoes and earthquakes. Anything planetary they control. That's about 100 years in the future. A few thousand years in the future is type 2. They can play with stars, just like Star Trek and the Federation of Planets. They can also ignite stars and play with stars. Then you have a galactic civilization, like the Empire of The Empire Strikes Back, or the Borg of Star Wars, a galactic civilization that roams the galactic space lanes. Now, what are we on this scale? We're type 0.
Right.
We're not even on the radar screen. We get our energy from dead plants, oil and coal. But, we are making the transition to type 1. The Internet is a type 1 telephone system. We actually see the emergence of a type 1 telecommunication system. English is the emerging type 1 language. The European Union, NAFTA, the beginning of a type 1 economy. And we see the beginning of a type 1 culture, rock and roll, high fashion, blue jeans, youth culture. We're beginning to see a type 1 culture evolve on the planet Earth. Now, when you see the movies and you see these aliens from outer space whizzing by, you can actually categorize what civilization type they're in. Buck Rogers and Flash Gordon would be type 1. The Federation of Planets in Star Trek would be type 2. And Star Wars would be type 3.
And by the way, everybody that's listening out there, if you want to learn more, Mr. Kaku's new book is The Physics of the Impossible. And it's at every bookstore everywhere, and I highly recommend it, reading it. I mean, it's just a phenomenal thing. I've got it in my hands here now, and I'm ready to go to the next level now.
Right.
One of my favorite, well, I want to kind of keep this going through, one of my favorite areas is antimatter and matter,
mm-hmm.
and dark matter and the energy in the Higgs field, mass feeding into to a proton. Where does it come from? What is the current view on dark matter and antimatter and mass coming from somewhere? I know people think that there's a lot of mass here, but like in your book you explained, for example, that if you took all the energy from the positive side of the universe and then you looked at the negative side, there's probably way more energy on the negative side, or maybe it would balance depending on, how you looked at it. So could you go into that a little bit?
People sometimes ask about parallel universes. We see them in Twilight Zone. And the new paradigm is that there could be parallel universes that are very similar to ours, but separated from ours in another dimension. If you think of our universe as a soap bubble, think of a soap bubble. We live on the skin of the soap bubble, and we're stuck like fly paper on that surface. We can't leave. The soap bubble is expanding. But we do believe that there are other soap bubbles out there, other universes that are being created all the time. And this is called the multiverse, a multiverse of universes. Now, believe it or not, we're going to be testing aspects of this theory in just 2 months. Outside Geneva, Switzerland, is the Large Hadron Collider. It's the largest atom smasher ever built in the history of the human race, 17 miles in circumference, and it will produce, we hope, dark matter. Now, dark matter is this mysterious substance which makes up most of the universe, except it's invisible. I mean, who would have thought that? Every textbook is wrong. Every textbook says the universe is made out of atoms. Well, that's not true. We now know that only 4% of the universe is made out of atoms, and 96% is made out of dark energy and dark matter, invisible energy, invisible matter. Who would have thought that? And we're going to produce it, we think, at the Large Hadron Collider in 2 months. Now, I work in something called string theory. In fact, I'm the co-founder of string field theory, one of the main branches of string theory. And string theory predicts that our universe that we see, the visible universe, is nothing but the lowest octave, the lowest set of vibrations of tiny little vibrating rubber bands. But this rubber band can have higher vibrations, higher particles. That's dark matter. So we hope to produce dark matter at the Large Hadron Collider. And if that's true, then I'm sure the Nobel Prize Committee will be just handing out Nobel Prizes to people who work in string theory. Because this could be the fabled theory of everything that eluded Einstein for the last 30 years of his life. So it's quite exciting. So in just 2 more months, we may begin the process of testing whether or not other universes exist, which is a prediction of string theory, and whether or not dark matter can be produced in a laboratory. This is incredible.
Yeah, they're a little late on building that thing, aren't they? I mean, it was too bad the way they scrapped the one that we were going to build here in Texas, but at least it's finally getting one built.
Yeah.
Are you going over there?
Texas. What?
You're going over there pretty quick, right?
Well, I was there 2 years ago. In fact, I visited the tube, which will eventually contain the proton beams as they collide.
Right.
But it's a real shame that the one in Dallas, Texas was canceled. That machine was canceled in part on the last day of hearings. A congressman asked a physicist one last question, and that was, will we find God with this super collider?
Right.
The poor physicist didn't know what to say. He said, we'll find another particle. So the congressman said, another particle? $10 billion for a god-darn particle? They canceled the machine.
Yeah, that's not very, very smart. That might have been the God particle.
Yeah, no, I would have answered it differently.
Yeah, I know you would. You'd have probably had it double the size of it, the way you talk.
Yeah, I would have said, I would have said God, by whatever signs or symbols you ascribe to the deity. This machine, the super collider, will take us as close as humanly possible to his greatest creation, Genesis. This is a Genesis machine. That's how we should have put it. But instead, we said another particle, and so they canceled our machine. Yeah,
that was brilliant. You know that. Just as I was going to New York the other day, it was Thursday a week ago.
Mm-hmm.
There you are on the History Channel.
Yeah. Mm-hmm.
And I didn't get to see what you were talking about. I said, there he is. I want to watch this, and I'm going to miss my plane. I can't. You've done quite a bit over there, haven't you?
Yeah, well, I work with the History Channel. They have what is called the Universe series.
Yeah.
And in fact, I just taped 3 more segments just a few days ago. And but I mainly work with BBC. They produce a lot of science specials that eventually air on the Discovery Channel and the Science Channel. So I do a lot of hosting for BBC television in England. And then eventually they sell it to Discovery and Science Channel and National Geographic.
Interesting. Yeah, because I wish I had to get a schedule, from somewhere, but you probably don't even know. They don't even know what
yeah, they don't even tell me. Yeah, they just put it on without my permission, so I never know what.
Yeah.
In fact, 3 days ago, I was on twice competing with myself. There were 2 stations running 2 shows that I was on. And again, they never tell me, so I never know this.
Yeah, you're going to have quite an IMDb rating here. You're going to have more than some big... it's really nice to have a person that's a outgoing personality, a figure skater, a physicist, a good sense of humor, and a great presence. I mean, I guess that's what you got to be to be successful these days.
Yeah, well, unfortunately, most physicists cannot talk, which is really sad,
You're right. You're totally right. They're just introverted too much.
Very introverted. And, there's so many questions that a physicist can make a comment about, like extraterrestrial intelligence or new particles being discovered, creation, new galaxies. There's so many things that scientists can talk about, but they're tongue-tied, unfortunately.
Yeah, they are. Now, I got so many things. Okay, now, psychokinesis.
Yeah. Okay, this is really new stuff, really exciting stuff. First of all, at Brown University, they took a stroke victim who is pretty much paralyzed, cannot talk, pretty much living in a shell. They put a chip in the brain, connected the chip of this paralyzed person to a laptop, and the person, after about 3 or 4 hours, began to move the cursor on the screen. And today, he can play video games with you. He can surf the web. He can write email, answer emails, and he's paralyzed. He does this strictly by thinking. This is astounding if you think about it. In the future, we may have tiny little chips implanted in our brains that are invisible. You can't even see it. No one knows you have it. And you could probably surf the web just by thinking about it. This is the power of this miniaturized chips that we can now access the brain with. And we can even begin to read certain thoughts. MRI scans can read the thinking brain. And when you tell a lie, it takes more energy than to tell the truth. To tell a lie, you have to know the truth, you have to know the cover-up, and you have to know the consequences of the cover-up. That takes a lot of energy. And you could pick up that energy on an MRI scan. More parts of the brain light up when you tell a lie.
Yeah, I know that they're looking at, in the MRI, there's a tremendous amount of electron activity, I guess, at the synaptic junctions when depending on what area, and it heats up, there's a heat signature that they look at, right?
Different signatures you can look for. Consumption of glucose, for example, can also be looked at.
Right.
So the MRI scans really see into the living brain. And in the future, we may even have a dictionary of thought. Certain patterns correspond to certain emotions. And this is going to go to trial later this year. There's a man suing his insurance company who denied his claims. The insurance company said, "You burned down your own store." He said, "I didn't burn down my store. I will prove it. I will have my brain scanned in court to prove I am telling the truth." So believe it or not, this is actually going to court now. This is pretty advanced stuff we're talking about.
Oh, yeah, it is. Yeah, I know when one of the, along the same line, when the phone rings and you know who is there, I've always explained it to people as a form of entanglement, between the person receiving the call and, of course, the person generating the call. And sometimes when you get entangled enough with people, you can just about predict a lot of things that they do.
Yeah, well, entanglement, Einstein hated entanglement. This is one of his big mistakes. He called it spooky action at a distance. But we actually measured in the laboratory. On this one, Einstein got it wrong. He was right most of the time, but he missed out on quantum entanglement, which, by the way, also makes possible quantum computers. Eventually, your laptop computer has a silicon chip will be replaced because silicon power will be exhausted by 2020, and Moore's law, the doubling time of computers, will collapse. Silicon Valley could become a rust belt by 2020, and we may have to go to quantum computers, which compute on quantum entanglement. So this very, very abstract phenomenon, quantum entanglement, may eventually be the computer architecture of the future. Even the CIA is interested. If you build a computer out of quantum entanglement, the computer can break any code known to man. And the CIA is very much interested in this.
Yeah, because they're already hacking into our Defense Department with the regular stuff. Somebody had one of those quantum computers now and got into our system, all these codes would be gone in moments, wouldn't they?
Oh, yeah, easily.
Yeah.
And so, quantum entanglement is a big business in the future, and there's so many applications, especially as we go to nanotechnology. Nanotechnology, of course, also uses quantum entanglement. And as I mentioned in the book, NASA, of all things, NASA is interested in these little nanoparticles because perhaps the starships of the future will be nanoships, ships that are about as big as a little needle, containing inside a whole computer inside that needle. And you shoot billions of them at the nearest star. Maybe only a handful arrive safely, but you don't care, of course. Each needle only costs a penny. And you send billions of them, and some of them actually make it to a nearby star. So NASA has even begun funding a proposal to build nanoships throughout the solar system. So this could revolutionize space travel. We don't have to have Captain Kirk and the Enterprise.
No, the other thing is the space elevator. I mean, I've been into that for a while, and explain that. That's like a something the size of a piece of hair that has 10 times the strength of titanium and steel.
Yeah, isn't that amazing? Arthur C. Clarke popularized it in one of his science fiction novels. This is Jack and the Beanstalk. Jack, as you recall, rode this beanstalk into heaven. Well, that's a space elevator. Why doesn't it fall down? Because of centrifugal force. If you have a ball and a string, why doesn't the ball fall down? Well, when you spin the ball on a string, centrifugal force keeps it afloat, even though gravity wants to yank it to the ground. So the Earth is spinning. It's spinning at about 1,000 miles an hour, believe it or not. And therefore, any rope that goes to heaven, if it's long enough, will not fall down. This is amazing. Now, you can calculate, in fact, we give this problem to our students, you can calculate that the tension on this beanstalk is greater than the tensile strength of steel. Steel will break. Therefore, Arthur C. Clarke didn't take it very seriously. But now, as you mentioned, with carbon nanotubes, they're much stronger than steel. They're made out of individual carbon atoms arranged in a tube. And now we're in business. Now it may be possible to reduce the cost of space travel. Space travel costs about $10,000 a pound. That's your weight in gold. Think of your weight in gold. That's what it costs to put you into orbit. If you have a space elevator, we may be able to drop that price by a factor of 100. This could make space travel accessible to the average person.
Yeah, that's interesting. I think that's phenomenal. I just wonder which way they're going to launch it, from the ground up, or they're going to drop it from the space down, you know?
Yeah, well, I think they're going to go from top down.
Yeah.
In the 1960s, there was a Russian scientist who did a calculation, and he said that top down is cheaper than bottom up.
Yeah.
But Tsiolkovsky, the famous Russian rocket scientist of 100 years ago, he thought it would be bottom up. He went to see the Eiffel Tower, and he envisioned the Eiffel Tower to the sky. That's how he envisioned it. That was the first mention of the space elevator in the literature, the Eiffel Tower to the sky. Now we think it's better to bring it down, bring down Sputnik and release a carbon nanotube fiber from outer space to the Earth.
Yeah, that would probably make more sense. We don't have to, we're using gravity in our favor at this point.
Yeah. Mm-hmm. And so, again, it's still decades in the future, but it's worth thinking about because the technology is almost there for a space elevator.
Yeah. Now, when going into, you know, the string theory itself and the parts that you're working on, I've often looked at the way DNA wraps up and winds up, and to me it's sometimes maybe DNA is like a macrocosm of how string theory, it might actually work. Could you elaborate a little bit on your work in that field and let people know how those strings work and intertwine and vibrate a little bit?
Right, yeah, there is an analogy. You see, DNA, you can contain an enormous amount of information, tens of thousands of genes in a tiny little fiber, all encoded on a string called DNA. So nature uses strings for very important things to store information. Now we think that an electron is not a dot. Every textbook says that the electron is a dot. But if you had a super microscope and could peer into the electron, you might find that the electron has structure, that it's actually a rubber band. And if you twang it and you change the frequency of the rubber band, it changes into a neutrino. You twang it again, it changes into a quark. And when I got my PhD at the University of California in Berkeley years ago, I had to memorize, I still remember this, the names of all the darn subatomic particles.
Well, that's a lot of hands. That's like a biologist would have.
That's right. There are hundreds of subatomic particles. I had to memorize the names of all these darn subatomic particles. I would hope that in the future, when you get your PhD in physics from Berkeley, all you will say is string theory.
Exactly.
You will get your PhD. Because all these notes that I had to memorize are just nothing but, A, B, C, D on a violin string. And that's why there's so many subatomic particles. So physics is now reduced to the harmonies of music.
Right, the music of the spheres.
Yeah, literally.
Yeah, I believe that. We have a product that a friend of mine, Randy Masters, I don't know if you ever met him or not. He used to teach over at University of Santa Cruz. Mm-hmm. He got into Balmer's work, and he makes these beautiful chimes, and they tune these things on the hydrogen atom frequencies, and they tune them with Hewlett-Packard spectrum analyzers to get them exactly accurate. And I played one on the Art Bell show the other night on George Norrie, and I got 1,000 phone calls. What was that sound? You know, I think when people can finally hear the strings vibrating in the string theory, I think a lot of stress is going to go away, and I think we're going to have like instant enlightenment.
Probably.
Yeah.
And, you know, we also even have a candidate for the mind of God. Einstein said that this theory will allow us to read the mind of God. These are his exact words. Well, we think that the mind of God could be cosmic music resonating through 11-dimensional hyperspace. We now have a paradigm to analyze the nature of everything there is. Now, the beauty of this, by the way, is that we may also be able to answer questions like, is time travel possible? And what happened before the Big Bang? So, string theory may be quite useful. It may answer the question whether or not time travel is really possible. Because in Einstein's equations, you actually have what are called wormhole solutions. That is a shortcut through space and time, just like Alice in Wonderland's looking glass. The looking glass is a wormhole. It connects the countryside of Oxford to this magical land called Wonderland, such that when you put your hand through the looking glass, it winds up on the other side of forever. Well, believe it or not, these are solutions of Einstein's equations. The simplest one is a black hole. When a black hole rotates very rapidly, as they do when we photograph them now, they collapse to a ring rather than a dot. Most textbooks say they collapse to a dot. The new thinking is they collapse to a ring. If you fall through the ring, you don't die. You fall through the ring, it's going through the looking glass. So the ring inside a black hole could be the frame of Alice's looking glass.
Yeah, and when what's his name that wrote that, he was a scientist too, wasn't he? Was a physicist?
Yeah, Charles Dodgson was professor of mathematics at Oxford University.
Yeah.
And he wrote under the pseudonym Lewis Carroll.
Yeah, Lewis Carroll. Yeah.
So string theory may resolve once and for all whether or not you can drill a hole through space and time, in which case that's much more efficient than using a flying saucer or a starship. You simply walk through a stargate and you visit the nearby stars that way. And it also may answer the question, what happened before the Big Bang? This is exciting stuff.
Sometimes I've often thought, and I'm sure you have too, that I looked at it from an archetypal level, thinking that, the planets are part of a, chakra system of a greater being, and that possibly God was maybe sleeping, and then he woke up, whatever God is, and that was the Big Bang. There's so many interesting metaphysical and physical ways to explore the beginning of the Big Bang. You predicted that, about 13.7 billion years ago, approximately?
Yeah, 13.7 billion years is the age of the universe. We know that because we can run the videotape backwards. We know the rate of expansion of the stars. We measure that with our telescopes. And you just run the videotape backwards, and you get 13.7 billion years. And then there was some people started making some gamma ray measurements, and they went out with about 330 light years or so to verify the age of the Big Bang. Is that, you know much about that? I'm sure you know a lot about that, but by looking at supernovas, you can begin to calibrate the age of galaxies, and the oldest galaxies we can see are 12, 13 billion years old, and the universe was born before that. So all the numbers are consistent now. And by the way, philosophically speaking, I find the multiverse idea very pleasing because it melds together Buddhism with Judeo-Christian thinking. Judeo-Christian thinking says there was a genesis, an instant of time when God created the universe. Buddhism says that there's nirvana, no beginning, no end, just timeless nirvana. Now we can blend these two theories together into a single theory. Now we have continual genesis, Big Bangs happening all the time, soap bubbles popping into existence like a bubble bath in a larger arena of nirvana, that is 11-dimensional hyperspace. So we now have a new picture, a bubble bath, continual genesis of a bubble bath inside a larger timeless arena called 11-dimensional hyperspace. So I find it very pleasing.
Yeah, I know that I think you kind of were an admirer, as I was, of Richard Feynman.
Feynman, right.
Yeah, he was out here for a while in California. And I remember I read something, I think it was in one of your books, about he was teasing this guy who was working on the 11 dimensions of the super strings and saying, what level are you on today?
Yeah, right. Very embarrassing.
Yeah.
Richard Feynman was a practical joker as well as a Nobel Prize winner.
Well, yeah, I think he wrote a lot of his papers in a strip bar, right? He was, when they, up there in Pasadena, he was quite a guy, you know?
Yeah, quite a guy. Yeah, he went to topless bars and things, but he had a very sharp physical sense. He was the leading physicist of his generation.
Yeah.
And he used to make fun of us string theorists by saying, well, how many dimensions are you in today, John?
But then he brought the chromodynamic theory out, which I studied that a lot a few years back. That was chromo-electrodynamics, I think it's called.
Yeah, he brought out quantum electrodynamics.
Yeah.
And now we have something called quantum chromodynamics.
Yeah, that's the one.
That's the quark model, basically.
Okay.
And the quark model works very fine. The quark model is a way to describe the proton as the combination of three quarks. So inside a proton you have three quarks, and inside a meson you have two quarks. The theory works very well. But then the question is,
that for me, you know, being a simple physicist, it really opened up the quark world and the hadron world a lot.
Sure did. And then the question is, well, what's inside a quark? Does it keep on going forever?
Yeah.
Well, if string theory is correct, the quark is nothing but one note of a vibrating rubber band, and it stops there. That is, there's no layer beneath the string. So it's pleasing because then we have a self-consistent system that the string is the smallest object in the universe, if this theory is correct. And like I said, we're going to be testing aspects of the theory this summer.
Yeah, I can't wait.
We're all quite excited, yeah.
So they must have some amazing detection systems. I know, and when you were in that thing over there, it must, I mean, working in a cyclotron lab like I did at the University of Michigan, that was tiny stuff to this new stuff. That was just amazing. I mean, it must be in that tunnel that's many, many miles long. What's it like over there when you're in that place?
You have to ride in an electric car to go from one point to another because it is 17 miles in circumference.
Right.
So to make repairs, you have to go in a car. Second of all, it will be radioactive, so they put it underground. The whole thing is underground.
Right.
So it's perfectly safe. And then the detectors are the size of skyscrapers almost. They're huge, gigantic detectors.
Wow.
A human being is like an ant compared to the size of the detector. And that's just the detector to detect the particles spewing out of the machine. So this is a huge device, but unfortunately it's in Europe, not the United States, and we have to beg the Europeans for time to get on the Large Hadron Collider.
Yeah. Well, you know, I mean, it's in your community, you know enough people. I'm sure they're going to want you over there.
Yeah, well, I'm a theoretician, so as soon as the data starts to pour out of that machine, people like me are going to analyze that data, and we're going to look for new exotic kinds of particles that give us a handle on Genesis and give us a handle as to whether or not string theory is the correct theory of Genesis.
Are you going to be writing, if someone more on the outside, because I haven't had the time to get back into that world, are you going to be writing some papers on this, and were they available to be read when the thing starts up?
Well, see, when the thing starts up, first they have to test the magnets just to make sure that all the electricity works in it, and so on and so forth. The beam won't be created till later.
Okay.
And even then, when they smash the beams together to create a huge array of particles when you smash protons together, that again will take about a year to collect all the data. When two protons slam into each other, you get billions of particles coming out, and you need a supercomputer to analyze all the debris coming out of this. But then again, that's what we think the Big Bang was made out of. So we have to study it. But boy, is it a mess.
Oh, yeah, I mean, that's got to be fascinating. You know, if you're like me, you're chomping at the bit for that first proton head-on collision.
Yeah. As I know, we're really up for it. In fact, we were taking bets 2 years ago as to whether or not the machine will produce dark matter, will produce particles or superparticles, another higher vibration of the string. If that's true, man, that's going to change the whole physics terrain.
Yeah, it is. The science in general will be different.
Yeah.
Yeah.
So that's why we're looking forward to it.
Yeah.
And like I said, it's going to be underground, so it's safe. You know, cosmic rays come from outer space that have even more energy than what the Large Hadron Collider produces. So it's a perfectly safe machine.
They're going to have a bunch of, what are they going to use, where are they going to power this thing from, in several different locations, or what?
Yeah, they're going to have they have their own a power station to generate it, because, you know, it consumes about as much energy as the city of Geneva. I mean,
well, yeah, I figured that, yeah.
It's a huge machine. You know, outside Dallas, Texas, we were to have our machine, a huge machine, even bigger. Congress gave us $1 billion to dig the hole for the machine, a big circle.
Yeah.
Then Congress canceled it, and they gave us a second $1 billion to fill up the hole.
Oh,
that's $2 billion to dig a hole and fill it up.
Well, that's about how our government works.
Yeah, how stupid.
Yeah, I know. Welcome to the United States. You know, I mean, I've been, I've worked in politics a lot too, and it's very frustrating, especially when you have a scientific background like both of us do, and you have to be around these politicians. It's scary.
Yeah.
And you ask them a question, and I've never seen, you could put them on a lie detector, they could tell a lie, and they could probably beat it because they would never answer it. It's amazing how they cannot answer a question in so many different ways.
Yeah, and when they tell an incorrect statement, they don't even know it's incorrect. So
no.
They're not even aware of that fact. Yeah.
No, another area that I'm just going to jump back into your book here again, because we're drifting all over the place, which is what I wanted to do anyway. Precognition.
Mm-hmm.
What do you, that's a real interesting topic. How much free will do we have, and I would assume that you're like me. You study the Eastern philosophies, may practice them, and so could you go on that a little bit, because you wrote a chapter on it? Yeah.
It's a whole other realm. You see, time travel, for example, we do think may be possible. In which case, what happens if you go backwards in time and meet your teenage mother before you're born, and she falls in love with you? How can you be born if you just met your teenage mother before you're born? Or what happens if you gave the stock market readings for the next decade to yourself as a young man? You could wind up as the next Bill Gates, because you know where the stock market is going. So all sorts of things could happen if you go backwards in time. So how do we resolve all these problems? Well, there's several ways to do it. First of all, Einstein said that time is like a river that speeds up and slows down. And as a consequence, we can measure these things in outer space. Our space satellites, like the GPS system, time slows down for the GPS system, and we measure that every day. In fact, the Pentagon cannot fight a war with the GPS system guiding its missiles unless we take into account Einstein's theory of relativity.
Right.
Now, the river of time can have whirlpools, we now realize. The river of time can fork into two rivers. Now, if the river of time forks into two rivers, and you go backwards in time and meet Abraham Lincoln at the Ford Theater, and you save Abraham Lincoln from being assassinated, what has happened is that you went from one time stream to another time stream. And so you didn't really save your Abraham Lincoln. Your past cannot be changed. You've changed somebody else's Abraham Lincoln, who's genetically equivalent, has all the memories of your Abraham Lincoln. So this means that you can change the past. It just means that you've changed somebody else's past. Your past, unfortunately, cannot be changed, or else you have a paradox, in which case you disappear. And we don't think that's a solution of Einstein's equations, just disappearing like that.
Yeah, I love the way that you put that, because I've explained, to some of my audiences about time. I say it's like a comet, and energy follows thought. So our reality of our joint reality of sharing time amongst the group that we're here, this world, is the now. There's nothing more than being here now. If we go back and try to stop Hitler or something, it's only an echo. I explain it that way. It's like an echo or a vibration of something. You can go back and have an experience with whatever that is, but that's not the timeline that we're in now. And it's nice that you bring up the physics equations to support that.
Right.
That's the beauty of being good in math.
Right.
I'm like Einstein. I was terrible in math. I had great ideas and could draw a great picture, but I hated math. Now I'm at my older age. I'm getting into it and starting to learn some of these equations, but I never really knew them. I just did what I had to do to get through class. You know what I mean?
I see. Well, the river of time, if it does fork into two rivers, gives us vindication of what is called the many worlds theory. The many worlds theory gets us back into, quantum entanglements that we mentioned before.
Right, exactly.
That our universe is vibrating at a certain frequency. But if this theory is correct, it means the universe can split. It can peel off other universes. The river of time can fork many times. And these other universes are no longer coherent with us. They have decohered. They no longer vibrate at the same frequency. So think of sitting in your living room listening to a radio. Your radio is tuned to one frequency. But in that room, you have Radio Moscow, all sorts of radio stations in that very same room that you are listening to, but you've decohered. You are no longer coherent. You don't tune into the other radio stations. Now, the same thing for reality. Everything around you is a wave. Everything around you is vibrating, but the other wave functions have separated from you a long time ago. So believe it or not, in your living room is the wave function of dinosaurs. In your living room, where you're sitting right now, the wave function of aliens, the wave function of pirates, the wave function of an Earth that never formed. Now, this may sound fantastic and incredible, but this is the way modern physics is formulated today. This is called the many worlds theory. String theory seems to agree with this picture. And it does mean that in one parallel universe, Elvis Presley is still alive. Some of our loved ones are still alive, except we have decohered from them, and we can no longer interact with them.
Right, that was some of Erwin Schroeder's, his cat.
That's right. This is the famous cat problem. How can you be dead and alive simultaneously? The way to be dead and alive simultaneously for an electron is easy. Modern electronics is based on this idea. Laser beams, the iPod, the Internet, this telephone conversation is based on the idea that electrons can be two places at the same time. But can people be two places at the same time? The answer is yes, if you have decohered with your twin. So there maybe is a universe where you have a brother and a sister that you never knew. Or perhaps there's a universe where you don't exist because your mother had a miscarriage. I mean, your mind goes bonkers thinking about these things.
Oh yeah, and then also thinking about when you go into the Big Bang, how and then like you're talking about the bubbles.
Mm-hmm.
I'm assuming that the energy to create that is so great that it becomes like a Planck length. It's just
this is for a Type 3 civilization.
Yeah.
A Type 3 civilization is galactic, and believe it or not, a Type 3 civilization may have enough energy to access the Planck length, to open a gateway, to open a hole in space and time, keep it open, so that you can walk back and forth without being crushed. Stephen Hawking and others have done the equations, and sure enough, it seems to work. So Stephen Hawking, my friend, has changed his mind. He used to say that time travel and all these things were impossible. He doesn't say that anymore. He now says that time travel is possible, but not practical. In other words,
he's changed a lot. He has.
Yeah, in the last 10 years, he's really changed his mind about some of the fantastic things that occur naturally in string theory.
Yeah, no, do you see him very often or not?
Yeah, but I saw him about 10, 15 years ago when he was still mobile.
Yeah.
I visited his house where he has mechanical contraptions that turn the page for him.
Yeah.
But it's very sad. He even lost that capability. He can only move his eyeballs now.
He needs that chip then, doesn't he?
That's what I'm saying. If we put a chip in his brain and connect that chip to a laptop, in 3 hours, he'll be answering emails.
Yeah.
But right now, he cannot move his fingers.
How does he communicate?
Through his eyeballs.
Oh, just that way.
Can you imagine? This is astounding.
Well, this guy, I'll tell you what, you talk about willpower to stay in this world.
Yeah.
He's amazing.
He tells jokes. He gives lectures. In fact, he's at Caltech right now. I was just at Caltech a few days ago. He's coming in a few days to Caltech. When he gives a talk, of course, he cannot physically give the talk. He has prepared the talk ahead of time,
right,
by moving his eyeballs.
And that's how he controls his computer, or what?
Yeah, well, he has to have a human there, and they have sensors that can read the motion of his eyeballs.
Oh, okay.
But can you imagine, typing the letters of the alphabet via your eyeballs? It's excruciating.
Yeah, that guy is out there, I'll say that,
Yeah, but, talk about willpower. But that's what it takes to get through to these. These equations are humongous, and that's what it takes to do that.
Yeah.
Power of the will.
Yeah, it's amazing. The other thing that I was going to ask you about, because we don't have much time left. A little bit more here. How many requests do you get? Every young physicist coming out of school that gets around the real guys like you wants to do something with a unified field theory.
Right. Yeah.
What do you get any really like wild things drop by in your office or in your throwing at you that kind of stretch your imagination a little bit? Some of these new people coming up or not?
Well, yeah, I get a lot of proposals in the mail.
Yeah.
In fact, I have 3 boxes in my office specifically designed for people with their own proposals. And on my website, mkaku.org, mkaku.org, I even have an article, about people who think they have the theory of everything.
Yeah.
If you think you have it, what are you going to do? How do you publish? How do you know if you have the theory of everything, right?
Yeah.
So I had to write an article as a guide for people who think that there's an next Einstein. Who knows? Maybe they are.
Yeah.
But you have to satisfy certain criterion that I put on my website.
So then you get people following that, meeting that criteria, or what?
Yeah, people try. They read the criteria and they try to conform to it. But again, the bottom line is mathematics. A lot of proposals have no math in it.
Yeah.
And for me, it's like writing about French civilization without knowing the French language.
Right. Exactly.
You really have to know the French language to speak to a Frenchman, right?
Exactly.
And the same thing here. We can talk about the beauty of nature and the mysteries of space and time, but the bottom line is, does it fit the data? You need an equation to verify that.
Yeah, that's true. But I just knew that you would be bombarded with those.
Yeah, I have.
Have any of the ideas actually been food for thought, or without hurting anybody's feelings or anything, or mentioning it, or?
Well, again, the proposals that I'd like to take seriously are the ones that have mathematics in it, specifically 5 years of calculus.
Okay.
But unfortunately, a lot of the equations are simply numerology,
Yeah.
This number looks like that number, this number looks like this number. Isn't that a coincidence? Maybe, maybe not. I don't know.
You got to have
theory.
Yeah, people don't understand Einstein was a visionary more than a mathematician.
Yeah.
But he had both.
Yeah, he had both. And, of course, he would ask the mathematicians to help him.
Yeah.
When he developed general relativity, he had the idea of space warp. He had that picture in his mind. But he cut class. He cut so many classes that he didn't know the mathematics of warp surfaces.
Yeah.
So he had to ask a mathematician, Marcel Grossman, to help him with the math.
Yeah. Grossman was I read some of his work. Pretty amazing stuff,
Yeah, so even Einstein had trouble with the math. He once talked to a bunch of junior high school kids, and
Yeah.
he said, quote, "No matter how great your problems are with mathematics, mine were greater."
Yeah, that I can relate to.
Yeah.
I just never could focus on that. So what's going to happen with you in the near future? What's your schedule? Are you still out on a book tour?
Yeah, I'm still in the middle of a book tour, going through Seattle and Los Angeles and San Francisco and Washington and Philadelphia and a few more places to speak. I'll be speaking at the Hayden Planetarium here. I was just at the Smithsonian last week.
Oh, I love that Smithsonian.
Yeah, it's great. And again, sellout audiences everywhere. So many people are curious about these things. So many people have seen Star Wars. So many people have seen the Star Trek series. And, they really want to know. And
yeah.
I think that's the time to grab these people.
Yeah, so how does it feel like to be a cosmological rock star? Is it good? Are you going to be taking? By the way, do you play a musical instrument?
Well, yeah, believe it or not.
Yeah.
When I was at Harvard, I played the trumpet.
Oh, that's what I wanted to play. I had a crooked tooth. I had to play the clarinet. You still play?
Well, I live in Manhattan now, and if I played the trumpet, I think I'd be sued by all my neighbors.
You got to get a mute. You know what those are.
Yeah, maybe I should get a mute. And I played the guitar, another string instrument.
Yeah, there you go.
Yeah.
The guitar ought to really help you get into, the string theory.
Yeah, that's right.
Yeah, and then eventually you can get a sitar and really rock and roll.
Mm-hmm. Right.
So when are you coming back out here to Los Angeles so I can come and watch you speak somewhere?
Maybe sometime in the future. Right now, I'm just kind of winding down, relaxing a bit as the book tour begins to wind down. But, it's on the website. You can actually see where I'll be speaking. Like tomorrow, I'll be speaking at a science fiction convention in Stony Brook. It's the famous Icon convention, so I'll be speaking there.
Oh,
and I'll be speaking at the Open Center in Manhattan, which is a center for holistic medicine. And then at the Hayden Planetarium
Oh, yeah.
And also the World Science Festival. There's going to be a World Science Festival in New York City. I'll be speaking there. And but again, all the schedule is on the web.
Yeah,
and
get
then
your website out again right now for everybody to hear it. Go ahead.
Yeah, it's mkaku.org, mkaku.org, and it gives you all the information you need.
Yeah, and I'll keep you up on our website for another day, and then I'll put something in there permanently. Because I think we need to, have everybody keep up with you. Because this is the health, science, and energy show, and you're the science part, and that's the most fun for us.
Right.
The health part's kind of boring. That's how we stay alive, so we can do the science.
I see.
We do a lot of holistic health over here. I got a PhD in homeopathic medicine now. That was my next career change after rocket science. We can't stop. I can't stop. I doubt that you can either.
Well, that's what life is all about, right?
Yeah, exactly. It's just the fruit of the. I don't know. My girlfriend really gets mad at me because I don't spend enough time with her. But I'm sure you've never heard that before. Well, anyway, I think we're just about out of time here. I really, really, really appreciate you coming on this show. And we'll do a rerun tomorrow night. I normally do a can show tomorrow, and I want to rerun this again because I got a lot of Saturday night listeners. And then I want to get you back on here again one of these days if you want to come back on when you got some more things to talk about.
Okay. Well, I'll talk to my publicist and I'll tell her, please give me a break.
Yeah, I know what it's like, and we'll wait till the fall or the winter or something. And then I bought a pair of figure skates. I haven't tried them out yet, but I'm going to start skating again after watching you. I mean, you're good.
Oh, well, thank you.
I can't do that. I'm about 1/4 where you're at. I used to be all right because I was born in Ann Arbor, but my God, you're good.
Oh, well, it's all Newtonian physics.
Yeah, it is. All right, well, I got to get off the air. We're getting kicked off.
Okay.
Thank you very much. You've been listening to Dr. Fred Bell's Health, Science, and Energy Show. Our guest has been Michio Kaku. We'll put more information up. And once again, we thank him for being on the show. Have a great evening, and we'll see you guys next Friday night.
Okay, bye.